All right, so get this figured out. All right, so before I came to NRL, my experience was in Eulerian split explicit time schemes and limited area models that use finite differencing, and I studied gravity waves. And so for the most part, this talk is about the troubles that I ran into when they asked me to work on a semi-Lagrangian global spectral model. And so basically, if you're familiar with our Eulerian model, which is no gaps, basically what we're doing now is we're changing it to semi-Lagrangian, we're increasing the resolution, and we're swapping out the physics. And so NavGem, the Navy Global Environmental Model, is a 3-time level, semi-implicit, semi-Lagrangian, hydrostatic model, spectral horizontal, finite difference in the vertical, and it's on hybrid pressure coordinates. And these are prognostic variables. Most notably, this virtual potential temperature is what I'm going to talk about today. So currently, we're at T359 L50, so just under 40 kilometer resolution, and we use a pretty conservative time step of 360 seconds. And even with the background that I had, I was very alarmed when I saw that it required a heavy implicit biasing, so a biasing parameter of 0.8 for stability. And so the big question that I wanted to answer was why? In large part because I knew if I wanted to study gravity waves, I would need to have some gravity waves, and this tends to go against that. So just for some background, so the semi-implicit scheme that we use is this classic Robert scheme that's been mentioned already. So you'll find this in most spectral models. Well, you'll find it pretty much all spectral models that you find out there. So we use some reference state, a reference pressure and frost theta, but we choose an isothermal. And so here we have our prognostic equations, and so we have our Coriolis terms, we have our height gradient terms, and so we consider these as our fast mode terms, and so we linearize about this reference state. And this delta TT parameter is described down here. So basically, this is our semi-implicit averaging. So we extract some linearized value and replace it with a semi-implicit averaging. So this alpha is our decentering parameter, which we would prefer to be centered. We want it to be 0.5. But as I mentioned, we needed it to be much larger. The question we want to answer is why. And so we have this system here. And if you go to spectral space, you can get a divergence equation out of this. And then we can do some algebra and reduce this to a Helmholtz equation of divergence. And then we can do an eigenvalue decomposition in the vertical of a mass matrix to solve it, to get our semi-implicit correction. So moving on from there, I started asking myself, okay, well, what are the stability conditions for semi-Lagrangian? One thing I should mention if I go back, that value of 0.8 for the decentering parameter, I should mention if we decrease that, model crashes. Okay, that's it, that's all. So we have to use that or larger. So semi-Lagrangian, we know we use it to get rid of the CFL condition. We want more efficiency. But we also get a new stability condition. We get this deformation CFL condition. Okay, we have to worry about the variation in the velocity. And so the worry there is if you have a lot of variation, then your implicit calculation to calculate trajectories will not converge. And the problem with that is that you can get these crossing trajectories. So here, if I just have some grid points, these are my arrival points. If I do my back trajectories, for these two cases, let's say my trajectories cross. Well, where they cross, that's a non-unique solution, and that's not allowed. Model's going to crash. So the semi-implicit scheme that I mentioned earlier, we use this to, we essentially slow down those fast modes that are preventing our efficiency, and we can use a bigger time step. So if I write this out for a 3-time level scheme for some prognostic variable psi, here's my Eulerian case, so I'm writing it symbolically. So I have my slope terms, which usually we consider advection, at this middle time level. And then we have our fast terms at the middle time level, and then we have our semi-implicit averaging, which is applied to the fast terms. So then if we go to semi-Lagrangian, it's pretty simple. We take our our slow terms, our advection, and we move it into the left-hand side. It gets absorbed into the trajectory calculation. And we're left with this equation here. So the issue at hand is, what happens if f and s are not separable? So if you're using potential temperature or a different conservative thermodynamic variable for your semi-implicit semi-Lagrangian, you might run into problems. So if you look at the energy conversion term, so this is the fast term in our potential temperature equation. So we'll look at a few different cases. In the thermodynamic equation using temperature, so you look at IFS, then potential temperature, so you got NavGem and the unified model. Or similarly, there's a model that uses enthalpy. So this is a semi-Lagrangian GFS that's in development right now. So here's the case. Here's what happens. So your fast mode term, if you use temperature, looks just like this. It's not an advection term. You have no choice to make. Okay? The F and S are completely separable, and they get a stable scheme. However, if you're using theta, or some variation, some conservative variable, your fast mode term is an advection term. So F and S are not separable. You have a choice to make. So basically, if you look at a time discretization that we get our total derivative on the left-hand side, and we get our linearized semi-implicit terms on the right-hand side. So if we took the term out, if we said it was a fast mode term, so just like the Eulerian case, perfectly stable semi-implicit scheme. You put it in the trajectory, unstable. It doesn't work. And this has been noted in Joy of UM for the new dynamics, that the lack of a semi-implicitly treated energy conversion term on the right-hand side results in an unstable semi-implicit scheme. So what options do you have? What can you do? Well, you can go the route that we were going when I arrived, which is you can try to use some reduced accuracy to get around it. So you know it's these fast modes that are giving you problems, so let's just wipe them out. So you use a really strong decentering, increase your diffusion, increase your time filter, whatever takes care of the problem. Or you can return that missing nonlinear term to the right-hand side. You choose to treat it as a fast mode rather than a slow one. And so some ways have been suggested for doing this. So there's a vertically non-interpolating scheme for theta. So this is in the UM's new dynamics documentation. And then also you could do semi-Lagrangian advection of a perturbation theta, which is in endgame. So the first route, this is actually a pretty clever way of doing things. It basically asks the question, well, how much do I need to treat it as a fast mode? Can I treat some small portion, or do I need the whole thing? So this tries the small portion route. So if this is my arrival point, and these are some vertical levels, I calculate a back trajectory. Here's my departure point. And what I'm going to do is I'm going to shift it to the nearest vertical level, and then I'll take this small portion and move it to the right-hand side and treat it in an Eulerian fashion. So if that worked, that would have been fantastic. It's stable in a linear stability analysis. However, it's unstable in practice. It's not enough just to move this small portion. And so the new dynamics needed a very heavy decentering, just like we did, to maintain stability. The next thing is you advect some perturbation theta. So this actually works out great with the setup that the UM had. It's got this predictor corrector scheme. It's got this iterative Helmholtz solver. And so what they can do is they can use the solution from the previous time step as their basic state. So they can keep this theta prime very small. And they can use the, so basically I'll give you an example down here. So you remove some basic state. So this is your new total derivative that you treat in a semi-Lagrangian sense. And then you advect the basic state using an Eulerian scheme. And they can do that semi-implicitly because of this predictor corrector method without worrying about CFL conditions. And also, they found a way through the iterative Helmholtz solver to reduce the dependence of the discretization on the choice of basic state. So that worked out really well for them, and I've seen some great results. However, I don't have all those bells and whistles. I had to find a different way to do it. So, in part, since our semi-implicit scheme forces us to use this theta v prime throughout our coupled equation system to solve the semi-implicit scheme, we have an opportunity to not only gain stability in our semi-implicit scheme, but to reduce error in the vertical integration of the geopotential gradient terms, and also to reduce this terrain resonance by including the terrain varying portion of theta v in the Eulerian advection. So the way we do this is I borrow an idea from most limit models, and also from a Woodall paper where they did this in CAM Eulerian, and they extract a hydrostatically balanced basic state. So for my purposes, since I do have to worry about CFL violations, I use a single vertical profile where I did a nonlinear regression to the US standard atmosphere, and I made it a function of pressure. So by making it a function of pressure, that's how I move this terrain influence to the right-hand side and try to reduce the terrain resonance. So how do my equations change? Well, these become perturbation quantities, these height gradient terms. The hydrostatic equation is now perturbation because I've extracted the basic state. And now I do semi-Lagrangian on this theta v prime, and I have an omega d theta 0 dp term on the right-hand side. And I can treat this semi-implicitly. So a few experiments. So first, did a single 1-month cold start comparing the control and this new version. Next, did some experiments where we varied the time step for both schemes. And then lastly, did long cycling tests with our 40 var DA system. And I'll show you some snapshots from that. So in all of these, some of the semi-Lagrangian details, so small details of interpolation, things like that, and some of the physics may change across these experiments, but it's always consistent between the two methods that I'm comparing. So first and foremost, Y.J. Kim, who provided these figures, was looking at a stratosphere warming case back in January 2011. And so he ran the control case. He just let these go for a month from a cold start. So here's the control case. Here's the perturbation theta advection. And these are monthly mean, zonal winds. And then down here is the NASA analysis. And so what you see is that in the control case, and I should mention, control case, as I said, decentering alpha 0.8. Here I've decreased it to 0.6. Why am I not using 0.5? I'll tell you in a minute. But what you see is that relative to this analysis, you see structure-wise, we get a dramatic improvement once we get to, say, 10 millibars and above. Specifically, we see that the jet pattern is closer to the pole. We get this open lower wind area here, and we get this hook pattern as well, whereas all that's sort of washed out in the control case. So we thought that was encouraging, you know, besides the fact that this was stable with a lower decentering. So when we saw that improvement aloft, we handed this code off to our space science division, our upper air guys who are interested in stratosphere, mesosphere, and we had them do some experiments, see what they thought. And so they ran this T239L60 control case. They were looking at zonal winds at 1 millibar just after 9 hours. And so here's the case with a time step of 360 seconds. And here's the case with 450 seconds. And what you guys maybe can't see is there's this really high frequency sort of ringing in the jet. And it gets worse here. And they also ran a case with a time step of 600 seconds, and it never made it to 9 hours. It crashed. And if you look at the differences between these two runs, what you'll notice, you see this high frequency noise. And if you look at the differences over here, they range up to 80 meters per second, just by changing the time step from 360 to 450. So clearly, bad things are going on here. If we go to the perturbation case with alpha equals 0.6, here's the time step of 360. Here's a time step of 600 seconds. Here's the difference. And differences are plus or minus 4 meters per second, which has been attributed to a stochastic gravity wave drag scheme. So it definitely worked in terms of stability, and I'm very happy with that difference. So the next thing I'm going to show you, let me go back a slide. So once this was sort of fleshed out as to what was going on here, what they found is, yeah, you're getting all sorts of crossing trajectories up here aloft, and that's what's causing you to crash. Well, so a limiter was put in to check for crossing trajectories and then modify as necessary to keep the model from crashing. So the next test I'll show you, so I went through and I cycled the control case, I cycled the perturbation case for 7 weeks, and I'm just showing you some snapshots from a forecast at the end of that time period. So 5-day forecast. So here I'm showing you the omega, pressure vertical velocity at 0.2 millibars. I went that high because that's where it was clearest. You can see it lower as well. And so this is the control case with the decentering and with limiters. And this, it's not supposed to look like this. So clearly you get all this numerical noise just like we saw in the previous test. The model doesn't crash. Clearly, I cycled it for 7 weeks and I'm running along forecast. It doesn't crash, but it doesn't, limiters don't fix the problem. They just stop the crash. So then if you run the perturbation case, so now I've decreased the decentering even more, 0.55, no limiters, and I love this picture. This is exactly what I want to see. I got my gravity waves. I don't see any of this choppy numerical stuff. And most of all, being a gravity wave guy as well, I know that down here we have our gravity wave hotspot along this latitude band, especially here in the Drake Passage, coming off the Andes, and I've got all that. And the amplitude's great, and so I'm very happy with this picture. So advantages, limitations. So the semi-implicit scheme is stable and effective, works the way we would expect it to. It allows larger time steps without issue. We can reduce the decentering and keep those high frequency motions that are driving the stratospheric, mesospheric circulations. And I didn't show any figures of this, but we had much better agreement with satellite observations aloft. Limitations, my choice of a basic state is subjective and allows large variations in theta prime. So using it without a predictor corrector, as I tried to show with my semi-implicit scheme, I'm basing it on some reference state. And so I'm always leaving behind some small explicit, well I hope small, explicit nonlinear vertical advection term. And so that can give me CFL violations over steep terrain. And so if I don't use some small decentering, I see noise over Himalayas, the Andes, and so that's why I need that small decentering. Just to give you, basically I said I'm worried about the subjectiveness of this theta prime. Well, what's the structure? Here's a zonal mean structure, just a snapshot. So, sorry this picture is kind of ugly. So where should my profile be best? Well, I picked the US standard atmosphere, and so my scale's a little bit small here, but basically all these reds, plus or minus about 100. Okay, so theta is going to be really big up here typically, so I'm happy that I'm keeping it relatively small. But then where does it get big? Well, it gets really big, you know, several hundred, nearly 1,000 when I get to the South Pole up in the mesosphere. So my theta is really big, and then if I look, well, where are my main differences in theta in the analysis after I've cycled for 7 weeks? So the perturbation theta minus the control. Well, my biggest differences are up here. So how is that related to my choice of basic state? Or is it just so happened that because I've decreased the decentering and I've got all these gravity waves, and this is a gravity wave hotspot, that I'm heating things up more? How is that related? That's something I need to investigate more. So application of a standard semi-implicit semi-Lagrangian scheme to some conservative thermodynamic variable leads to an unstable centered scheme. So if you want to get back a stable centered scheme, then you have to extract this vertical advection or whatever your fast mode term is that's embedded in that trajectory and treat it in Eulerian fashion. So results show significant improvements for us above 10 millibars, where the decentering was most detrimental beforehand. So future work, as I said, I want to try to create a more uniform theta prime. And also, once we move to a 2-time level scheme, it'll be more feasible to try a more implicit method. So I'll stop there.
The departure point calculation usually has an impact on this kind of instabilities. I wonder, what do you do to compute the trajectories? Do you use the standard extrapolation, time extrapolation technique, or you do something else?
No, since it's a 3-time level scheme, well, we're just using the standard implicit iteration. So it's, yeah, we're not doing the extrapolation like in a 2-time level scheme. No.
Some time ago, it's a very big thing how to choose the representative temperature,
Right.
Especially on the global model. And I think that the technique for a semi-implicit model, global model, is to choose a reference temperature that's larger so that all the perturbations are negative. Otherwise, it's like treating a diffusive-like term in the wrongly sampled fashion. So even though it's counterintuitive, because you would say, "Oh, I would like it to be like my mean state," you have to choose it biased so that all the corrections are negative. That's one of the reasons that most of the semi-implicit model use a very large temperature.
Right, but do you mean the reference for the semi-implicit scheme or the reference for what I'm trying to do, which is this?
The reference for the semi-implicit.
Right, and my semi-implicit reference is pretty standard. It's I didn't modify that from what it was before, and I haven't seen any. Well, the stability's there. I'm not seeing stability issues with that.
2 more questions.
It seems that your problem would go away in a vertical Lagrangian coordinate. Is that an option you would consider?
I've not looked into it, but I was actually looking at a poster earlier today where I was like, that's pretty interesting, because yes, it seems like it would.
I didn't follow it all in the detail, but compared to IFS, you're using potential temperature, and in IFS we use temperature.
Right.
And I'm wondering if you're missing a term in the semi-implicit right-hand side of the temperature equation because of that. Shouldn't there be an extra term related to the surface pressure, which may actually cause you problems? I'm, rather ad hoc, but maybe we could talk about this.
Offhand, I'm caught off guard by that question. I don't. My answer is I don't think so, but we can talk about it more.
Okay, thanks for your answer.